Greetings from MWN.com. Dr. M. Wilson, formerly Vice Principal and Head of Department of Commerce, Scott Christian College, Nagercoil is delighted in presenting this session. Thank you. Please subscribe the channel MWN.com. Chapter 20. Statistical Quality Control. Statistical quality control is a technique to control the quality in a manufacturing company. In order to control the quality, the standard in each category of production should be determined. For example, standard weight of a component part is 350 grams. Like that, the standard for all the component parts or products should be determined in advance. But in real production, the exact standard could not be achieved. There will be some variations from the standard in the large quantity of production. The variations may be at high level or at low level. If the degree of variations is high, then the quality of the parts manufactured will be affected. Hence, there is a need to determine the acceptance level of variations on the higher side and at lower side. The acceptance limit is based in the normal efficiency of the machines. The variations it gives in the normal conditions should be determined. This is called the upper control limit and lower control limit. It is determined through the output of the machine or process of production in normal conditions. It can be determined through selecting sample outputs randomly and examining the variations in that. The sample of few items for many times is selected and measurement should be done for fixing the control limits. For example, in the production process 50 or 100 samples of the output may be randomly selected for more than 100 times for measurement. The selection of items and the number of times of selection depends on the nature and type of products and machines and processes. On the basis of the selection and measurement, the upper control limit and lower control limit can be determined. After fixing the control limits, it is the duty of the production manager to see that the quality of output would be within the control limits. This method of controlling the quality is called statistical quality control. There are many methods for determining the control limits. Control chart. Control chart is a graphical representation of the upper control limit and lower control limit. A model of control chart is given as follows. Types of control chart. There are various types of control charts to control various aspects relating to a manufacturing process. They are as follows. 1. Control charts for mean, X-bar chart. 2. Control charts for variation, R chart. 3. Control charts for standard deviation, small sigma chart. 4. Control charts for number of defects, C chart. 5. Control charts for proportion of defectives, P chart. 1. Control chart for mean chart. It is based on arithmetic mean. In the quality inspection for quality control, samples are randomly selected for many times, say, 50 items may be selected for 15 times. The selected samples are measured to determine the control limits. It helps to identify the normal quality of output. The control limits are upper control limit and lower control limit. After determining the limits, it is expected that the units of output should be within the two control limits. Mean or X-bar chart is one method of calculating the control limits, that is, upper control limit and lower control limit, and drawing a chart based in the control limits. The control limits are calculated on the following basis. Since many items are selected for many times, the average, X-bar, weight or length, etc., of each sample should be calculated. Hence, there will be many averages based in the number of times the samples are selected. Hence, average of the averages, X-double-bar, grand mean, should be calculated. Then the standard deviation of the averages should be calculated. The calculations should be applied in the formula meant for the determination of the control limits. The following is the method of calculating control limits in this method. Formula for X-bar and X-double-bar is mentioned here. X-bar is the average of variables. That is sum of all the variables divided by the total number of variables. X-double-bar is the average of averages. That is the sum of all means divided by the total number of means. Small x equals X-bar, X-double-bar. The control limits are calculated as follows. Illustration 1. The quality controller of a company randomly selected 9 parts for 12 times to determine the control limits. He measured the length and the average length of the 9 component parts for 12 times, and the details of it are stated as follows. Here 12 averages have been given. Solution. Calculation of double X-bar, grand mean and standard deviation. 4 columns table should be prepared. In the first 2 columns, values is given in the illustration should be written. Then the sum of the 12 means is given in the second column should be added and divided by 12. That is 33.5. This is called X-double-bar or grand mean. In the third column, the means in the second column should be deducted by the grand mean, that is 33.5. then the square of these values should be written in the last column and sum of these values should be calculated. The square root of this value divided by n, that is 12, is called standard deviation. On the basis of x bar, x double bar, that is mean and grand mean, and standard deviation, upper control limit and lower control limit can be calculated. It is represented in the following chart. Illustration 2. The weight of each 4 component parts randomly selected for 10 times are stated as follows. Draw a control chart for mean. Solution. Calculation of double x bar, grand mean and standard deviation. 9 columns table should be prepared. In the first 5 columns, values is given in the illustration should be written. Then the sum of the 4 variables in columns 2, 3, 4 and 5 should be added and written in the 6th column. Example 24 plus 29 plus 24 plus 27 equals 104. Like that, all values in the rows should be calculated. Then all these values should be divided by 4 to know the mean, that is, x bar, and should be written in the 7th column. Then all these values should be added, that is 225. And divided by 10 since there are 10 means, that is 22.5. This is called grand mean. In the 8th column, the means in the 7th column should be deducted by the grand mean, that is 22.5. Then the square of these values should be written in the last column and sum of these values should be calculated. The square root of this value divided by n, that is 10, is called standard deviation. On the basis of the above calculations, upper control limit, UCL, and lower control limit, LCL, can be calculated. The control limits are represented in the following diagram. Illustration 3. Draw a 2 sigma and 3 sigma control charts from the following. Grand mean is 27 grams, standard deviation is 5.7, and the number of samples is 15. Solution. 1. Control chart for 3 sigma. Upper control limit, UCL, grand mean plus 3 into standard deviation divided by square root of n equals 31.41. Lower control limit, LCL, grand mean plus 3 into standard deviation divided by square root of n equals 31.41. Grand mean minus 3 into standard deviation divided by square root of n equals 22.59. The control limits are represented in the following diagram. 2. Control chart for 2 sigma. Upper control limit, UCL, grand mean plus 2 into standard deviation divided by square root of n equals 29.94. Lower control limit, LCL, grand mean minus 2 into standard deviation divided by square root of n equals 24.06. The control limits are represented in the following diagram. 2. Control chart for range, R chart. The difference between the largest and the smallest values of a sample of observations is defined as the range. It can be denoted as R. Since many samples with many items are selected for the analysis, there will be many ranges. Hence, the average of it, that is R bar, should be calculated to determine the control limits. The calculations for control limits in this method are as follows. R bar equals sum of R, that is all ranges, divided by number of R, that is ranges. Upper control limit, UCL of R equals D4 R bar. Lower control limit, LCL of R equals D3 R bar. The values of D3 and D4 can be known from the appendix table. Control chart for mean and range. The lower and upper control limits through mean and range can be determined through the following formula. Upper control limit, UCL equals grand mean plus A2 R bar. Lower control limit, LCL equals grand mean minus A2 R bar. The value of A2 can be known from the appendix table. Illustration 4. The weight of each 5 component parts randomly selected for 10 times are stated as follows. Draw a control chart and find out the 2 control limits based on range. Solution. 7 columns table should be prepared. In the first 6 columns, values is given in the illustration should be written. In the 7th range, that is R, should be calculated. Difference between the highest and lowest values are called range. Example for serial number 1, the value 35 is the highest and 27 is the lowest, and hence the difference is 8, which should be written the last column. Then the sum of these values should be calculated, and if divided by 10 is known as R bar. That is 66 by 10 equals 6.6. Calculation of control limits based on R bar. R bar equals 6.6. UCL R equals D4 R bar equals 1.777 into 6.6 equals 11.73. LCL R equals D3 R bar equals 0.223 into 6.6 equals 1.47. Value of D4 as per table for n equals 10 is 1.777 and D3 equals 0.223. The control limits are represented in the following diagram. Illustration 5. The following are the X bar and R values for the 10 samples of 5 readings. Draw control charts based on X double bar and R bar. Solution. Calculation of X double bar, that is grand mean and R bar. 3 columns table should be prepared. The values is given in the illustration should be written. Sum of the values given column 2 and 3 should be calculated. The average of these values are called X double bar, that is grand mean and R bar. On the basis of this values, upper control limit and lower control limits can be calculated as follows. The control limits are represented in the following diagram. On the basis of this values, upper control limit and lower control limits can be calculated as follows. The control limits are represented in the following diagram. 3. Control charts for standard deviation, small sigma chart. This chart is based in the standard deviations of the randomly selected samples. It can be prepared after calculating the control limits on the following basis. Upper control limit, UCL equals B2 small sigma. Lower control limit, LCL equals B1 small sigma. Small sigma indicates standard deviation. If small sigma is not given, then the average of the sample standard deviations should be applied. In such a situation the formula is as follows. Upper control limit, UCL equals B4 S bar. Lower control limit, LCL equals B3 S bar. S bar is the average standard deviation of the samples. The values of B1, B2, B3, B4 can be known from the appendix table. Illustration 6. Prepare a control chart when the standard deviation of the samples of the production process is 9.7 and the size of the sample is 10. Solution. Small sigma equals 9.7 and n equals 10. Upper control limit, UCL equals B2 small sigma equals 1.584 by 9.7 equals 15.36. Lower control limit, LCL equals B1 small sigma equals 0.262 by 9.7 equals 2.54. Value of B2 as per table for n equals 10 is 1.584 and B1 equals 0.262. The control limits are represented in the following diagram. Illustration 7. 10 samples with 40 readings showed the following standard deviations. Prepare a control chart based on small sigma. Solution. Total of standard deviations equals 129.7. Average of SD equals 129.7 by 10 equals 12.97. Upper control limit, UCL equals 1.716 by 12.97 equals 22.26. Lower control limit, LCL equals 0.284 by 12.97 equals 3.68. Value of B4 as per table for n equals 10 is 1.716 and B3 equals 0.284. The control limits are represented in the following diagram. 4. Control charts for number of defects, C chart. This method is based in the number of defectives in each sample selected for study. It is denoted as C. Since many samples are elected for the study, there will be many C. Hence, the average of it should be calculated to determine the control limits. The calculations for control limits in this method are as follows. Upper control limit, UCL equals C bar plus 3 square root of C double bar. Lower control limit, LCL equals C bar 3 square root of C double bar. Illustration 8. The number of defects identified at final inspection of the 20 buses manufactured in a company are as follows. Prepare a control chart for the number of defects and state whether the process is in a state of statistical control. Solution. Sigma C, that is total of C equals 290. The control limits are as follows. UCLC equals 14.5 plus 11.43 equals 25.93. LCLC equals 14.5 11.43 equals 3.07. The control limits are represented in the following diagram. Since all the points are within the control, the process is in a state of control. Illustration 9. The number of defects identified in the output of a product for 10 days is as follows. Solution. Sigma C, that is total of C equals 32. The control limits are as follows. UCLC equals 3.2 plus 5.37 equals 8.57. LCLC equals 3.2 minus 5.37 equals 2.17 equals 0. Since LCL could not be negative value, it should be considered as 0. Since some of the points are outside the control limits, the process is not in a state of control. 5. Control chart for fraction defective or proportion of defectives, P chart. This chart is based in the proportion of defectives in the production process. The allowed limit of fraction or percentage of defectives should be determined on the basis of the study by selecting many items in many times. The many times is called number of samples. The fraction of defectives in each sample is determined on the basis of number of items and the number of defective items in it. Suppose 50 items are selected in the sample and 7 are found to be defective, then the fraction in that sample is 0.14750. All such fractions in all samples should be calculated and then average of it should be calculated to determine the control limits. The calculations for determining the control limits in this method are as follows. P bar equals total number of defectives in all samples divided by total number of items inspected in all samples. The upper and lower control limits are as follows. If lower control limit is less than 0 minus value, it should be considered as 0. Illustration 10. A quality inspection about the production of component parts by a machine is conducted by selecting 50 samples randomly for 15 days. The samples were checked to find out the defective or non-defective parts. The number of defective items found, in each of such samples, is stated as follows. Draw control charts based on P bar. Solution. Total defectives equals 65. It is the sum of all values in the second column of the table given in the illustration. Total number of items inspected equals 15 x 50 equals 750. Total number of defectives in all the samples equals 65. Hence, P bar equals 0.087. Thus, upper and lower trial control limits for proportion of defectives are UCLP equals 0.087 plus 0.12 equals 0.207. LCLP equals 0.087 0.12 equals 0.033. The control limits are represented in the following diagram. Since the lower control limit is negative value, it would be considered as 0. Illustration 11. A quality inspection about the production of component parts by a machine is conducted by selecting 40 samples randomly for 10 times. The samples were checked to find out the defective or non-defective parts. The fraction of defective items found, in each of such samples, is stated as follows. Draw control charts based on P bar and determine the control limits. Solution. Total proportion of defectives equals 1.73. Thus, upper and lower trial control limits for proportion of defectives are UCLP equals 0.17 plus 0.18 equals 0.35. LCLP equals 0.17 0.18 equals 0.01. The control limits are represented in the following diagram. Since the lower control limit is negative value, it would be considered as 0. Illustration 12. In a sample of 50 with 120 items randomly selected shows that the average fraction of defectives is 0.25. Calculate the control limits and draw a control chart. Solution. P bar equals 0.25, n equals 50. Thus, upper and lower trial control limits for proportion of defectives are UCLP equals 0.25 plus 0.18 equals 0.43. LCLP equals 0.25 0.18 equals 0.07. The control limits are represented in the following diagram. Control chart for number of defectives. Control chart in fraction or percentage give values for upper control limit and lower control limit in fraction. It may be difficult to draw control charts if the fraction is very low. Hence, control charts for number of defectives are drawn through the following formula. Average fraction defective, sigma P bar equals sigma P by n. Average fraction defective equals NP bar. The control limits are calculated as follows. Illustration 13. The number of defective parts identified in a production process by selecting 150 parts at a time for 10 times 10 samples is stated as follows. Draw control charts based on and determine the control limits. Solution. Total defectives equals 110. Average fraction defective, P bar equals 0.073. N equals 150, NP bar equals 150 by 0.073 equals 11. Thus, upper and lower trial control limits for proportion of defectives are UCLP equals 11 plus 9.57 equals 20.57. LCLP equals 11 9.57 equals 1.43. The control limits are represented in the following diagram. Sampling inspection. The statistical quality control related to preparation of control charts is for controlling the quality in the production process of a company. Consumers are always concerned with the quality of the items they receive from the supplier. Normally, the goods are distributed to consumers through middlemen like wholesalers, retailers, or agents. Hence, it is the duty of the middlemen to check the quantity of products they receive from the manufacturers. If the supply is not of good condition, then they can return the lot to the manufacturer. In the checking of quality, it is possible to check each item if the quantity is of small size. But if the quantity is of large size, then it is not possible to check each item. Hence, there is a need for selecting few items randomly and to check the condition of it to decide whether to accept the lot or not to accept it. The process of checking the quantity with randomly selected few items is called sampling inspection. Hence, sampling inspection is the process of checking the quality with randomly selected few items to decide whether to accept the lot or not. Acceptance sampling. There are 3 types of acceptance sampling plans. 1. Single sampling plan. 2. Double sampling plan. 3. Sequential sampling plan. 1. Single sampling plan. In this method, a sample of n items is drawn from a lot containing n items. The lot is accepted if the number of defectives in the sample is less than or equal to the acceptance number, C. If the number of defectives D is equal or less than C equals accept the lot. If the number of defectives D is greater than C equals reject the lot. For example, in the consignment of oranges, 10% defective is permitted. If the lot contains 1500 oranges and 70 oranges are randomly selected, then the randomly selected oranges should equal or less than 10% of 70 defective oranges for acceptance. If the sample has more than 7 defectives, then the lot can be rejected. 2. Double sampling plan. This method is based on the assumption that the selection and inspection of the sample at one time may not give correct result. If the selection is biased, i.e., non-random, then the result may be wrong. Hence, this method states that samples for 2 times should be taken and the decision about acceptance or rejection can be taken on the basis of the number of defectives. If the total number of defectives is within the acceptance limit, the lot can be accepted. Otherwise, it can be rejected. It can be represented as follows. N1 equals first sample size, N2 equals second sample size. D1 equals the number of defectives in first sample. D2 equals the number of defectives in second sample. C2 equals acceptance number of defectives in the 2 samples. If the number of defectives D1 plus D2 is equal or less than C2 equals accept the lot. If the number of defectives D1 plus D2 is greater than C2 equals reject the lot. For example, in the consignment of oranges, 10% defective is permitted. If the lot contains 1500 oranges and 70 oranges are randomly selected and it was found that 9 oranges are defective. Then another sample of 100 oranges is randomly selected and it was found that 7 oranges are defective. Hence, the total defective oranges are 16, that is, 9 plus 7. The lot can be accepted since the defective oranges are within the acceptance limit of 17 defectives, 10% of 170. 3. Sequential sampling plan. It is otherwise called as multiple sampling plan. It involves examination of a sequence of units, or group of units, of a lot chosen at random. In this method, samples for 3 or more than 3 times are selected to determine whether a lot is to be accepted or rejected. The examination is to be done more than 3 times to get full confidence in the decision of the distributor. Exercises for this chapter is well presented here. Exercises for this chapter is well presented here.